Standard migrations rely on application layer plugins. These run inside the PHP execution environment, which is constrained by strict memory limits and execution timeouts. When migrating a large Elementor portal, these plugins often freeze mid-transfer or trigger 500 internal server errors. Shifting the migration to the infrastructure layer allows the operating system to move the data while bypassing PHP entirely. This provides a systems-level environment that guarantees the transition executes exactly as planned, preventing layout corruption and keeping downtime to near zero. Executing this method requires specific technical access. You need root SSH permissions, WP CLI installed on the server, and a target virtual machine provisioned with a minimum of 4 vCPUs and 8 GB of RAM. Moving the operational load to the compiled utilities of the Linux shell protects the data. The underlying foundation remains stable throughout the move, regardless of how the WordPress application behaves. Elementor's CSS regeneration process is memory-intensive. At the standard limit of 128 megabytes, the worker process typically runs out of memory and aborts a queue mid-execution, resulting in an unstyled page. Increasing that limit to 512 megabytes provides the necessary overhead for the server to process the entire queue. For shared media mounts, we must configure the network file system, or NFS, using specific flags in the fstab file. We set nconnect equals 8 to increase storage concurrency, and then append the noac flag to the sequence. The noac, or no attribute cache flag, ensures every node in the cluster sees file updates immediately. This prevents the system from freezing due to a stale file handle, which occurs when a client attempts to read an old cached version of a directory that the visual editor has already deleted and recreated. Before the move, we audit the source files for integrity. Running the WP core verified checksums command in WP CLI confirms that the WordPress core files match the official versions and haven't been compromised or corrupted. We also lock down the file system permissions on the target server, enforcing a strict 755 rule for directories and a 644 rule for files prevents 403 forbidden errors from blocking the site after the DNS propagates. Hardening the server plumbing and verifying file integrity before moving a single byte of data eliminates the silent configuration drift that creates errors in standard moves. We migrate the application files using iterative rsync commands to copy the data in the background while the live site remains active. During this sync, we strategically exclude the WP content/uploads directory, since that data is already handled by our NFS mount. Traditional gzip relies on a single CPU core, creating a bottleneck for large archives. We replace this with the multi-threaded Pigz utility. Pigz parallelizes the compression across all available CPU cores, allowing us to handle massive site archives in minutes rather than hours. The database is migrated using MySQL dump. We execute this with the single transaction flag, which allows us to dump the entire database into a single file without locking the production tables or interrupting live visitors. Immediately before touching the target database or altering DNS records, we create a file system level snapshot using LVM or ZFS. This snapshot provides a safety net that allows for a near-instant rollback to a known good state if the cutover fails. Combining background multi-threaded data syncs with instantaneous file system snapshots creates a controlled execution window where data integrity is protected at the hardware layer. Our governance model enforces a strict separation between teams. The infrastructure team manages the blue system state, while the development team handles the orange application logic. The items bridging the gap in the center, the IPs and credentials, are the only points where these scopes overlap. Elementor stores button padding, hex codes, and typography as length-delimited PHP strings. If a manual SQL update changes a URL but doesn't update the character count in the metadata, the PHP engine finds a structural mismatch and fails to read the data. This breaks the entire visual layout. To protect the layout, the development team must use serialization-aware WP CLI commands. We run WP search replace to update text while recalculating array lengths, followed by WP Elementor replace URLs for internal metadata. Finally, we execute WP Elementor flush CSS to rebuild the physical style sheets. With the styles rebuilt, we transition to day 2 operations. The infrastructure team removes the noasac flag from the fstab file. This restores standard caching behavior, reducing latency and lowering the strain on the NFS server. We also deploy the Elementor CSS Regenerator plugin to monitor for 404 errors. If an update causes style sheets to vanish, the plugin automatically rebuilds them in the background, so the cache delivery remains uninterrupted. Respecting PHP serialization formats via dedicated command line tools ensures the visual presentation layer remains intact throughout the infrastructure transfer. Verification begins in the browser's Network tab on the new target domain. We check for 0, 404, or 500 errors and confirm that the regenerated CSS is being delivered immediately to every visitor. This strategy successfully bypasses PHP execution timeouts and eliminates NFS staleness. By restricting database updates to WP-CLI, we have also removed the risk of serialization corruption. You can find the specific shell commands, CLI flags, and NFS configurations used in this framework in the migration cheat sheet linked in the description below. Relying on shell-level utilities and deterministic engineering ensures that high-traffic portals move between environments without compromising site stability. This infrastructure-led approach provides the technical precision needed for long-term architectural control.